Welcome, welcome. We are back with the RI seminar today. It is my great pleasure to introduce Guanya Shi, our very own. Guanya is an assistant professor here in the Robotics Institute. Guanya received his PhD from Caltech in Control and Dynamical Systems. Before that, he was a postdoc at the University of Washington. And I have a list here of some of his important awards, so I don't forget them. Guanya has gotten the Themutis Discovery Prize, the Ben C. Chow Doctoral Prize from Caltech, Rising Star in Data Science, and an Outstanding Student Paper Award finalist at RSS. So with all of this, we're super excited to have Guanya today here to talk to us about building generous robots. Go for it.
Yeah. Oh, you can clap after actually. Yeah, I will start after people get sick. Yeah. Right. There's something like called popcorn theory. Like you start a talk after like this, you know, the number of new people convert to 0 or something like that. Anyway, all right. I think I will get started. Very excited to be here in the RI seminar today, presenting some of our recent research. You know, I feel like I'm taking the home court advantage as an internal speaker because next week I'm gonna visit Michigan, right? Let's go, Tartan. Yeah. So the title of today's talk is building generalist robot with agility via learning control, humanoids and beyond. Here are some teaser videos. The first one is humanoid robotic control called Omni-tool. The second one is sampling-based multiple control for contact range problems. The third video is safe high-speed locomotion. We will get into detail later. All right, let me start by talking about some recent trend in general purpose robot. It seems like in recent years, general purpose robots are really taking off, especially humanoid. Right? There are many investment, big companies, and startups, right? Here's just like a partial list of humanoid companies, right? There are really a lot. And there are also a lot of big players like NVIDIA and Tesla, right? You know, like Tesla also released some new things yesterday, right, for Optimus. So what is a general purpose robot? Well, a common definition is robot that can do many different tasks in many different environments. For example, here are some humanoid skills from the Omni-tool and Overcoco project. It's like same robot that can do very diverse tasks, right? On the top left, it can play tennis. On the bottom left, it can interact with people, give you a hug or shake hands with you or say bye. And on the right top, it can dance. On the right bottom, it can do this parkour kind of jumping stuff, like jump like continuously 2 times. Right, you can argue for all these applications, there exists some robot maybe can do better than humanoid, but humanoid is general purpose, right? It's one robot can do all these different tasks. Another example is, right, a very famous mobile Aloha from Stanford, right? It's basically a mobile manipulator that can do many different tasks, right? It can cook shrimp for you after you eat the shrimp. It can raise the pan, and it can high five with you, and it can push the chairs, right? It can do a lot of different tasks in kitchen and household applications. Yeah, it's very exciting because it's general purpose. So in my opinion, there are 2 axes or aspects defining such kind of useful general purpose robot. So one axis is the so-called generalist aspect. The x-axis, the brown axis in this figure. So basically that's the breadth in task or environment diversity. Like task diversity refers to how many tasks the robot can do. And environment means like what kind of environment it can do tasks. For example, like different kitchens or various terrains for like a robot. Another axis, in my opinion, is agility aspect. Basically the depth in the task execution. For example, like how fast the robot can do the task, and dexterity, precision, and reliability, right? I may abuse the word agility a little bit here because agility here not only include the physical agility, they also include, you know, something like how reliable, how precise the robot can do this task. So ideally, we want to boost, right? Ideally, we want to boost agility and generalists, right? And in this plot, each bar here corresponding to some environment, some task, right? We basically want all of these environment tasks better than human. Human performance is this dashed line, right? So yeah, we want both breadth and depth. So this is very, very interesting because in other fields like natural language processing, I think language model already achieved that, roughly speaking, right? If you think about language model, it outperforms classic method, even human, in many different tasks, right? You know, historically in NLP, for translation, for summarization, you have different methods. And today, you know, a single language model can do summarization, translation, stuff like that, better than this classic method, better than human. How about robotics? Can we cover both a generalist and agility? And there seems to be some trade-offs, at least into this research, right? On the one hand, right, there are many amazing works focusing on agility side, right? Agile robotics in some specific task, but with limited generalizability, corresponding to the plot here, right? For example, let's start from our own. Back in 1990s, almost 35 years ago, Professor Chris Atkinson and Stephen Shaw already achieved this humanoid juggling. It can juggle like 3 balls here. Very impressive, still very impressive today in my opinion, right? And this is like first-person view, very agile, very precise, right? And also like this devil stick juggling. I don't think I can do that. Yeah, so it's very agile, very precise. Remember, it's 35 years ago almost. Another example is, you know, this high-speed in-hand pen spinning from the Ishikawa lab in University of Tokyo, right? Please pay attention because the first few seconds of the video is real time. It's really the pen is spinning very fast. This is real time, first few seconds, right? And this is slow motion. You can see the 3 fingers really cooperate very nicely with each other and it's so smooth. Yeah, this is also like almost 20 years ago. It's very agile, very precise. And it's vision-based, by the way. There's no like kind of state estimation from mocap or whatever. And another example, I'm sure everyone knows, is Boston Dynamics human parkour, right? Again, it's super agile and parkour for the Atlas, a full-set humanoid, right? And this is slow motion, it's very precise, very agile, and I think it's still one of the few humanoid that outperform human in terms of agility. Okay, however, right, this method in general have limited generalizability. For example, if we zoom in here, what happens is, right, the same robot that can do parkour can also make this interesting mistakes, right? In this video, Atlas thought it got the card, but actually it didn't got the card, and it fell, right? It's corresponding to this, yeah, it's corresponding to this short bar in this plot, right? It's like in the parkouring, it's doing amazing job. If you switch the task a little bit, performance drop a lot. So on the other hand, right, we have also amazing progress in the generalist work, right? System like corresponding to this figure, right? All the bars are kind of okay, pretty good. Like system like robotic transformer RT theorists from Google DeepMind can do many different tasks, right? In this video. Wow, this is probably why figure 1 in robot learning papers are getting bigger and bigger because you have so many tasks to show off. But however, I would argue like most of the tasks in the video are not very agile, or like much less efficient than human, right? Grasping takes like 20 seconds, right? Things like that, right? This is like so many tasks, right? Can do like thousands or hundreds of tasks. Very impressive. So an interesting question you may want us to ask is, can we get here? Can we get superhuman or close to human performance using scaling law by collecting many different data? And I don't know. Maybe yes, if we have like enough data. But the problem is, in the near future, we wouldn't get GPT level amount of data, high quality data in robotics. All right, so this is like, I present 2 kind of examples, agility with limited generalizability and generalist with limited agility. So how to build generalist robot with agility? That means something there, right? We have a robot that can do many different tasks and all very agile, very efficient, and very safe, very precise. So it is a very challenging problem, which apparently I cannot tackle today, but I would like to share some written thoughts with you today. So in my opinion, on the agility axis, physics and dynamics really matters. And so the first key idea of today's talk is better use of physics and dynamics. So can we combine learning with structures and ideas from model-based control and physics to achieve something called a structure scaling? That's something I've been thinking about recently. And on the generalist aspect, I think scaling really matters. but it's not just how to scale, also what to scale. So the second key idea of today's talk is better use of scaling. So the robot learning community has focusing a lot on offline scaling, offline learning. So how about online scaling? Can we also scale like online adaptation, online planning, online optimization? So this is basically like two key ideas of today's talk, or like take away message. So great. This is like today's talk's technical outline. Like remember this figure, it's very important. And in the first part, we're gonna introduce like versatile humanoid full body control using sim-to-real model-free reinforcement learning. Because in my opinion, sim-to-real model-free reinforcement learning is the easiest way to combine physics dynamics and offline scaling, right? Because you train the policy in physics-based simulator, right? And you collect a lot of data using PPU or whatever, and you transfer to the real world, right? You actually combine physics and offline scaling. And in the second part, we will discuss some limitations of such framework and how to go beyond it via learning control. Particularly, there are 3 different levels combining learning control, like have structures. The first level is dynamics level. It's learning dynamics from the real world. And the second level is policy level. It's like, how do we have a structure and hierarchical reinforcement learning and control? And the last one is program level. Is can we use ideas from learning to improve some control program like MPC, right? You're not learning dynamics, you're not learning policy either. You are kind of improve or enhance some existing control program using learning. All right, this is outline. And let's get started. Let's start the part 1, humanoid sim-to-real RL stuff. So the first project I would like to introduce is called H2O, human to humanoid whole body teleoperations. So the high level goal of this project is to build an interface between human and humanoid motion. Like we want to build a humanoid that can mimic whatever the human does, so-called whole body teleoperation problem. And specifically the goal is we want to use a single RGB camera to whole body teleop a full set humanoid. In this case, it's Unitrish one. Okay, before talking about the details, I would like to show you a video for the readout. So the robot. All right, this is a humanoid. So why is it hard? This teleoperation is not new, right? Like in tabletop manipulator or mobile manipulator, like mobile Aloha, people already done that. It's pretty easy. Like inverse kinematics is all you need. Why is it hard for humanoid? So it's hard, like exactly from these 2 aspects. In the agility aspect, it's hard because you want to handle ad-dimensional whole body control problem, which requires upper lower body coordination. And on the generalist aspect, you need the humanoid to track infinitely many diverse human motion in real time, right? Because you want a very strong generalization, right? Because human can do whatever he or she wants, and humanoid need to respond. So the key idea of H2O is basically, as I said, scaling sim-to-real reinforcement learning from large-scale retargeted human motion data set. That's the key idea of H2O. So how do we do that? There are 3 steps. In step 1, we create a large-scale humanoid feasible motion data set. So in computer vision and computer graphics community, there's already a very good data set called AMAS. It gives us a lot of human motion sequence, like in this figure. So the question is, can we simply just do inverse kinematics to convert this AMAS data set to shape-fitted SMPL motions, right? So this red body here is the shape-fitted SMPL model closest to humanoid. And the red is the unitary H1 humanoid. So what I mean is you first find some SMPL human motion model and do inverse kinematics, right? You kind of mapping from the first row to the second row. Does that work? And unfortunately, no, because like some motions good for human may be invisible for humanoids, right? For example, the last one, kind of like acrobatic maneuvers, is absolutely not feasible for humanoid. And the second one, maybe, who knows? So basically, we need a dynamics level or physics level motion retargeting. We need like physics-based motion retargeting, not just kinematics level. So how do we do that? So the key idea of H2O is a procedure called simulation-based data cleaning. The idea is quite straightforward, actually. So what we do is we train a privileged imitation policy, the pink guy in this figure, to imitate and track all the motions, right? It's basically like trying to follow this second row here, right? And why it's called privileged policy? Because it knows everything. It knows everything available in the simulator, including those not available in the real world, like how other state, for example, like angular acceleration, things like that, like angular velocity, yeah, of each joint. So once we do this, we generate the humanoid feasible motion, the last row here, and we filter out impossible motions, right? Like last one is impossible, we just filter it out. Yeah. So basically, this procedure gives you a dynamics aware humanoid feasible motion data set using this privileged imitation policy. So once we have this data set, the second step is sim-to-real reinforcement learning. And we train a deployable policy, the blue guy on this figure, right? And the blue guy takes 8 key points as the motion goal, 8 key points from the data set. And this policy is practical, right? Why it's called deployable? Because it only knows robot states available in the real world, right? It only knows this practical state. It doesn't know this higher order kind of state. And also for sim to real, we did a lot of domain randomizations for robustness. For example, here we added terrain randomizations to perturbable terrain. We also add a lot of perturbation force and torque just to make this policy robust, deployable in the real world. This is the second step. Basically, you train a deployable policy, right, with available information in the real world. And the third step is quite straightforward. After you have the deployed policy, what we do is we use off-the-shelf like algorithm from the vision community called Hybrid to get human pose as a point cloud. And then we use from RGB camera. And then we use this deployable policy to track the eight key points from this pose point cloud. Yeah. And the tracking, the pose estimation is 30 Hertz. The sim-to-real policy is 50 Hertz. Right. Yeah, and that gives us this kind of the video in the beginning. So H2O, right, is, in my opinion, actually the idea is quite straightforward. It's 3 steps, right? It first do dynamics aware motion retargeting, and then do sim-to-real reinforcement learning training, and finally achieve real-time teleoperation. And there are some limitations, right? Maybe you already noticed in the video, we have some latencies. The humanoid doesn't immediately respond because one of the reasons is we use RGB camera. RGB camera is own interface. It has some delays and also some errors. And also the current pipeline requires 8 key points, like 2 shoulders, 2 elbows, 2 hands, and 2 ankles. For many like teleoperation device, you don't have so many key points. For example, if you want to use Apple Vision Pro or VR device, you don't have like ankle or like kind of elbow information, right? And also we don't have a hand. It's just humanoid. We don't have like hand. And also like it's purely teleoperation, right? We don't have any autonomy. So we basically handle all these limitations in the following up paper called H2O, which enables universal and dexterous H2O with autonomy. So H2O enables low latency and precise teleoperation with dexterous hand. It also enables very diverse human control interface. It's not just RGB, it's also VR like Apple Vision Pro and verbal instruction. It's also give you some autonomy, either via learning from demonstrations using diffusion policy or integrate with foundation model like GPT-4o. And by the way, this project is fully open source from training to hardware deployment. Everything is open source. And as Europe, before the technical detail, let me play a video. So the first thing is all right. Check out the website for like detail of these videos. So what's delta? What is the main technical change from H2O? It's mainly two things. The first is we augment the image data set with standing and squat motions, like C and D below, like the last two below, just to make it more stable, to make it better for some manipulation task. So the second thing is we give up RO for the deployable policy part. We instead using teacher-student framework, supervised learning to learn a deployable policy. If you remember previously, we trained this pink so-called teacher policy or privilege policy using RO. We trained this student so-called deployable policy also using RO. And here in this paper, we use Dagger. Once we learn this once we learn the teacher policy, the privilege policy, we Dagger to distill it to a deployable policy. It's supervised learning problem. Yeah, that enabled much more stable training. And also we use much more sparse motion goal. Previously in H2O, we have 8 key points, and here we only use 3 key points, 1 head and 2 hands. This make it more flexible for different teleoperation interfaces, like Apple Vision Pro. Yeah, this is what we use is this 3 points, 1 head and 2 hands. Yeah, for the finger part, there's no RO or control. It's just inverse kinematics. Yeah. All right. So another product of Omnis2O is the first humanoid whole body demonstration data set. We call this Omnis2O 6 because this includes 6 tasks. It includes some interesting whole body tasks like squatting, moving baskets, stuff like that. And this is like a video showing the result using learning from demonstrations. We use diffusion policy to train a policy from demos. To be honest, this is still very. All right. As you can imagine, you can also integrate the Omnis2O with multimodal frontier models like GPT-4o. So here we have a very simple prompt to tell GPT-4, okay, you are the humanoid. There's a human doing something from the vision, and you should do something. Yeah. And in this video, Taran, want to shake his hand with robot, and robot shake hand with him. Yeah. You may notice a latency, but that's pretty much from API latency from GPT-4o. We are waiting for GPT-4o's output. Yeah. Again, the interesting thing is that because humanoid is very like human, the prompting is very simple, right? Because you don't need to tell the GPT-4o, okay, humanoid, if you quadruped, it's a lot more tricky, right? The minimum embodiment gap between humanoid and humanoid make this thing easy. All right. So this is like omnitrol. The last project I want to introduce in part 1 is Vococo. So each tool basically try to learn from human motions, and the Vococo is basically the opposite. We're trying to learn versatile and agile whole body skill without any human motions, right? The Vococo full name is learning full body control with sequential contact, right? Because in many scenarios, we don't have human motion reference, right? You can only learn from yourself. So again, before the details, show a video. Vococo enables very diverse full body skills, like this parkouring simulation, or to some kind of like wake parkouring in the real world, like continuous jumping on the stairs. And we also did some funny clamping dance. I think there should be background music. Apologize. Yeah, this is like whole body kind of clamping dance. And this is like some interesting bidirectional cliff traversal. It's basically, we want to prove you need upper lower body coordination to do this kind of task. And this is like moving a box to another location. It's basically a local manipulation problem. You need grasp a box, move to the other location. All right, many different tasks. Yeah. All right, what is the key idea? So the key idea is, again, from generalist aspect, the main challenge is different tasks need either task-specific, very tedious reward tuning or very strong motion priors, right? The reward you use for parkouring is very different from dancing. So how do we tackle the challenge is we realize all the tasks can be decomposed as a sequence of contact goals and task goals. Just to give you some examples, this is like the previously mentioned parkouring task. You can actually decompose this long horizon task into like 5 stages. And each stage, you have some contact goal, have some task goal. For example, in this particular stage, for a contact goal, you want to establish contact between the right foot and the stepping stone, not left foot, right? This is the contact goal. And the task goal for this frame is you want to like upper body either like hug or relax, right? These 2 goals define this kind of stage. It's actually inspired from model-based planning. And once we have this composition, right, we can decompose a very long horizon task into many context stages using this diagram, right? And move from context stage 1 all the way to context stage I. And we basically learn a conditional policy, pi, condition on this sequence of contact goals and a sequence of task goals. This small I here refers to the current contact goals and task goals. And the big I here means the horizon, how many stages there are. So basically the main like benefit of this decomposition is this enables task agnostic, very general reward and training data. So in Vococo, all the tasks, parkour, dancing, local manipulation, they share the contact reward, exactly the same reward for all different tasks. The only thing you need to specify is so-called task goal reward. There's only 1 to 2 reward terms for each task. So it's very general. The contact reward is shared by all the tasks. Unfortunately, I don't have time going into details, but check out paper if you're interested in Vococo. All right, this is part 1. We showed a bunch of interesting demos. Let's go to part 2, how to go beyond this via learning control. So why? Because I want to start from some discussions. Do we still need model-based control? Because in part 1, seems like everything is pretty interesting, right? All the demos in part 1 are trained with model-free end-to-end sim-to-real reinforcement learning, like H2O, omnitrol, Vococo. So the results are pretty interesting. But if we take a deeper look, this is what happens on the generalist agility plot, if you still remember the plot. So in simulation, everything is pretty good. We may have some tasks totally fail. Maybe it's PPO exploration issue, maybe it's overfitting, whatever, but in general, it's okay. But if you do the same true transfer, a lot of weird things could happen. For example, like all the tasks basically performance drop, but some tasks will just completely fail. Yeah, This could be from, sim to real gap, could be from, fragile to perturbation. So yeah, this is, really what happens in my lab. Yeah, students are struggling on that. Actually, nobody likes this kind of sim to real transfer. Okay, in my opinion, the current sim to real pipeline have some fundamental issues. Like the policy are sensitive to training environment. Like you change the simulation parameters, you change the seed, even the result is completely different. And the sim to real gap is large, unintuitive, and hard to quantify. You never know which task give you bigger or smaller sim to real gap. And in general, this procedure requires very tedious reward tuning, curriculum tuning, and domination tuning. In general, it still requires GSD, graduate student descent. There's no principles of theory, whatever. And it's hard to encode prior physics. This procedure suffer from poor sample complexity. And of course, there's no guarantees. And another thing very interesting is this whole procedure, we don't have any deployment time improvement. Once you learn the policy from the simulation, you're done. You fix the policy. There's no online fine tuning, online improvement. Yeah, I think this is really some fundamental issue. So I think we still need model-based control, and we should get best tools. Again, as I said, today I'm gonna give you some insight on 3 different levels very briefly. And the first level is dynamics level. Can we combine learning control, like learning dynamics from real world and do model-based control? Or learning a word model, if you prefer, obviously. And the second level is policy level or action level. Like rather than doing end-to-end learning, can we have some structure? Can we do structured and hierarchical reinforcement learning control? And the last level is program level. It's basically, again, you are neither learning dynamics nor the policy. You are trying to enhance control program like MPC using learning. So in my opinion, the role of control here is threefold. So first, it brings structures or priors from physics and dynamics, which matters a lot for agility. And second, it can guarantee or enhance safety, robustness, or efficiency. The third, in my opinion, is very interesting, is it allows some kind of test time scaling via online adaptation, online planning, or online optimization. Again, I think robot learning community has overly focused on offline scaling, not on online scaling. I think combining with control is a good way to bring online scaling in some sense. We will get into this later. All right, let's start from the dynamics level, right? The key idea is you learn dynamics from the real world. And the first example I want to present is my PhD work, a little bit old, called neural control family. So the key idea is, okay, we consider this Euler-Lagrangian dynamics in the black part in the equation. However, there's some residual dynamics, which is unknown, right? The F part is the so-called residual unknown dynamics, right? Which is, for example, like turbulence or whatever. So the key idea is we use a deep neural network, collect data in the real world, and to learn a model to approximate F. Once we learn this model F hat, which is an approximation of F, we design nonlinear controller pi as a function of F hat. And we need some design, right? We need some design for F hat. For example, we need to bound its Lipschitz constant to guarantee the optimal stability. The threshold is specified by control theory, which I'm not going to detail today. But the takeaway is you need to regularize learn dynamics from control theory to make sure the system is stable. And this is some applications. In a single agent case, we have a neural lander. In this case, the F hat is basically the ground effect force. If you fly a drone close to the ground will have ground effect. And in multi-agent case, the F depends on neighbors. And we also can learn this multi-agent dynamics. And in the adaptive control case, F is time variant, it changes over time. And we're basically using meta-learning to learn representation and use adapt control to fine-tune this in real time. So this works pretty well. So after joining CMU, I'm thinking about how to scaling this to something like transformer. So that gives us a second example called any car. So in this project, we're basically trying to learn a universal dynamics model for all wheeled robots. So basically the goal is to learn a transformer-based dynamics model that can adapt to all different types of cars, all different types of environment, all different types of state estimations via in-context adaptation. We will get into that later. And once we have this model, we use the sampling-based MPC for control. And this is all the different terrains, different cars, this model can adapt, and also different state estimation. I want to emphasize this This white tear here is not standard tear. We 3D print a plastic tear to challenge the model's adaptation ability. This is 3D print, very bad tear. Okay, and before talking about how we train this model, I want to show you some results. With this learned model, we can enable like drifting in the wild. So the car is actually doing drifting using this 3D print plastic wheel in the wild. Yeah, and this is also like pre-rapid adaptation. It can adapt from grass to land to concrete. Yeah, this is also using some of the stuff. And this is like adaptation. One model scenarios via in-context adaptation. So how do we train this? So the NAK model is basically a sequence-to-sequence dynamics model. The input is K step, noisy state action history, and H step, future action. And the output is H step, future state, right? It's basically a sequence model. You take like H step action, you want to query, it gives you H step prediction, right? So the first step trains model is data collection. We really get a lot of inspiration from like training language models. There are two phases, pre-training and fine-tuning. So we collect a lot of simulation data, 100 million for pre-training. This simulation data is very diverse, from very simple simulation to Mujuko, to SXM, all the way to F1 level car simulation. Yeah, from the left to the right. It's very diverse simulation data, 100 million. And we pre-train the transformer. Once we pre-train the transformer, we fine-tune it using a small amount of real-world data. So we collect some real-world data, like just 20K, right? With the estimator and the mocap pairs, and for fine-tuning. And this is how we train the model once we have the data. So this is basically a standard transformer structure with all the elements in language model. Basically, we have a tokenizer, we have position embedding, everything. But interesting design is we need some robustness for training. We basically basically did some mask out. We randomly mask certain element in the history. We also add Gaussian noise. We also add some like large attack. All these are trying to make the model robust. All these are trying to mimic what happened in real world state estimation and trying to make it robust. Right. And again, the K here is pretty large. It's 500. It has a 500 history. And each here is 100. So it's a very large transformer-based dynamics model. Okay, this is a dynamics level. The takeaway is you learn dynamics from real world, and do model-based control often give you interesting and very good behavior. And the second level is policy level. The key idea is rather doing end-to-end reinforcement learning, can we do structured and hierarchical reinforcement learning control? And the first example I want to present is this agile continuous jumping paper. So basically here, reinforcement learning, in this figure, it doesn't directly control the robot. It only generates like a high-level center of mass reference trajectory, like the Q double dot ref. It doesn't directly control the robot. So once we have this like a high-level reference from RO, we have another QP-based controller trying to optimize so-called ground reaction force. So it's basically a hierarchy. The high level, you have reinforcement learning, give you reference point. The low level, you have MPC to track this reference point. And that gives us very agile, continuous jumping over stepping stone, right? I think this is for the first time, a quadruped can continuously jump over stepping stone. And we also enable this kind of all this parkour stuff. It's also, the model is adaptive from the flexibility of RO. If the gap is too wide, it decides to take a middle step. If the gap is like smaller than 80 centimeter, it's just one step jumping. Yeah, it's adaptive. And this, is actually fully on board and autonomous. We use depth camera for sensing. So the input to reinforcement learning is actually directly the depth camera. All right. And this method, I think for the first time, enable this continuous jumping over stairs. This is like actually a stairs in University of Washington. Like here, you can see the robot actually has some stumble, but quickly can recover because MPC layer, the QP layer is very robust. And we can also enable this like agile parkour stuff. The robot can continue to jump over a big kind of like stepping stone. We actually compare with some recent robot parkour learning papers. There's some papers here. Generally speaking, we can enable much faster because we are doing jumping. And we can also enable like continuous jumping over stairs. And also the head is much higher. All right, this is like the structure and hierarchical RL control. Another important application of hierarchical and structured RL control is safe robot learning. And the paradigm is very similar. You have a high-level reinforcement learning and you have a low-level control. And in this case, low-level control is very specific. It's a safety filter. It's a safety filter to safeguard the potential unsafe reinforcement learning policy. I'm going to give you two examples. In the first example, the safety filter here is model-based. It's based on control barrier function. So basically, you learn a model and you use this kind of another quadratic programming to filter out this potential unsafe reinforcement learning action, pi theta. Yeah, and we can enable this car navigation. We have different payload. The robot can adapt or can do collision avoidance with the middle hazard area. And this is model-based. And the second example is model-free, based on learning reach avoid value function for safety. And the problem of model-based safety, like CBF, is it requires like the model is linear, it's ifan, and it cannot scale up to high-dimensional system. So here we are using model-free, like reach avoid value function for safety. So the key idea is given a potentially unsafe policy, we learn the reach avoid value V pi RA. And this value function basically is a kind of like thresholding. If the value function is smaller than epsilon, meaning that the policy is safe, you can just go ahead, execute the policy. And if the value is bigger than this threshold, that means the policy is unsafe. And we execute a recovery policy to lower the value. Yeah. And as shown in this figure, right? The green is the agile policy, potentially unsafe, and the red is the recovery policy. And the switching between them is governed by the learned reach avoid value function. And the whole procedure is kind of model-free, because all you need is a black box model. You don't need to assume it's linear or whatever, and it is scalable to high-dimensional system. And this is the performance. The quadruped can have very fast collision avoidance in narrow corridor, different terrains. And by the way, this is fully open sourced, and it's safe and robust. And all the computation on board and autonomous. We use depth camera as the same thing. And it's very robust in winter Pittsburgh, which is harsh. Different terrains. It's very reactive. Okay, I'm gonna skip to my favorite part. Yeah, I can do a lot of different obstacles, and it's also very reactive. Like if you swing your leg, it can dodge in real time. You swing your leg, it can dodge. You can even play this hide and seek game with the robot. Yeah. Okay, the key takeaway is hierarchical and structured RL can also be safe if you have some control kind of structure. Yeah, at the safety filter. All right, last part of today's talk, which is last level, program level. So like basically enhance multiple control user learning. Again, in this part, we're neither learning dynamics nor learning the policy, but kind of enhance, accelerate existing multiple control program. So to make sure we're on the same page, let me introduce the standard MPC formulation. So MPC is basically solve this H-step optimal control problem. And C is the cost function, X is a state, U is a control. And the big U here is a control sequence, is the decision variable. Then the most important thing in MPC is the so-called receding horizon strategy, right? So at every time step, once we solve the U, we only take the first action. We only execute the first action. The next time step, we resolve another MPC problem, right? This receding horizon strategy is very important. So the main challenge of MPC is this problem is hard to solve. Like solving this problem is in real time is really challenging, especially when this problem is highly non-convex or highly dimensional. For example, for contact-rich problem, your F is not even continuous, right? This problem is obviously non-convex. Or if you have nonlinear dynamics, if you have like complex reward function or whatever, this problem is highly non-convex. So, let me give you some examples to further illustrate why it could be challenging, especially for gradient-based method. Let's think about this case. This is like basically how you play the game Angry Bird. It's very similar. So basically in this problem, we want to throw a ball over the wall. The velocity is fixed. The initial velocity is fixed to be V0. All you can control is the angle, theta, right? and you want to throw the ball as far as possible. And the right-hand side is the cost function, GU. The G is basically the shooting distance. The x-axis is your control yield angle, right? You want this as low as possible. In this figure, right? So as you can see in this landscape, this problem is definitely non-convex. It's not even continuous, right? So you can imagine gradient-based method will struggle or fail, right? Because it's discontinuous case, right? This problem also happens for contact-rich, like manipulation, like locomotion. This dynamics is not continuous. So sampling-based MPC, like MPPI, is alternative, but it is with limited agility and little theoretical understanding. To make sure we're on the same page, let me introduce the MPPI for you very quickly. So MPPI is one of the most popular sampling-based MPC method. It's actually pretty straightforward. What it does is you sample an uncontrolled sequence from a Gaussian distribution centered around current control, centered around U. And the covariance sigma, you have these n different samples. Then what you do is you rule out these samples to evaluate the cost, J1 all the way to Jn, right? And once you have this cost, you compute the weight using this kind of the softmax, right? We can safely call Nobel Prize winning equations, right? Because it has deep connection with Boltzmann machine and energy-based model, right? Yeah, right. You basically, but intuition is here, right? The lambda is temperature, and the higher cost this sample has, the lower weight you're going to assign to this sample, which makes sense. Lambda is the temperature. And once you have the weight, the last thing you do is you generate the output, right? The output is basically the weighted sum of all the samples, right? Again, the better performance the sample has, the higher weight you're going to assign to this sample. And this is how it works. Some visualization in practice for parkouring. You can see all these trajectories are samples, and the red trajectory means lower cost. The white trajectory means higher cost. All right. So to understand MPPI and to improve MPPI, I need to introduce some notations, unfortunately. So I need to introduce two distributions. The first one is called target distribution, P0. The definition is proportional to exponential to minus G over lambda. This is basically the desired distribution corresponding to G. We are interested in the maximizer, right? The maxima of this P0, right? Again, this P0 is still non-convex, still discontinuous. And another interesting distribution is called P sigma. That's basically like a corrupted version of P0. More specifically, P sigma is a convolution between P0 and the sampling kernel Gaussian, right? The star here means convolution. And here I showing 4 different P sigma. The P1 is corresponding to the smallest sigma that gives you a still very stiff distribution. And the P4 give you a large sigma, right? After convolution, the distribution become very smooth. You can think of P sigma as a way to convexify or smoothify the P0. Okay, this is some notations. So what do we prove is the following result. So MPPI is actually doing something very similar to diffusion. We proved the following result in our recent news paper. As number of samples goes to infinity, the output from MPPI is actually U plus sigma multiplying the score function of P sigma. And again, the P sigma is the convolution between P0 and the Gaussian sampling kernel. So basically what that tells you is MPPI is a one-step ascent with a sigma condition score function. Again, this gradient of a log likelihood is called score function. Very important concept in diffusion model. So it is roughly doing a denoising step, right? And if you're familiar with Langevin dynamics in score-based diffusion model, it's very similar, right? In Langevin dynamics, it's doing something like this, right? The S theta is the learned score function, basically corresponding to the gradient of log P sigma. And the small sigma, right? Small sigma is the score network need to condition on noise level. The sigma is the noise level. The only thing different is in diffusion model, you have a wet noise. You have the wet noise Z after this score function because in diffusion model, you want a coverage, you want a diversity. But in MPPI, we only care about the max method. We don't care about the coverage. So you don't have this Gaussian noise. But it's very similar, right? And in mere data, we realize MPPI doesn't take a very important mechanism in diffusion model, which is annealing. So annealing is very important in score-based diffusion. So you always start from large noise and gradually anneal down to small noise, right? And in this figure, right, you start diffusion model from large sigma. You always all the way annealed down to small sigma. And that gives you very good performance. For example, in this paper from Youngson and Stephen Ehrman. Yeah, in image. So can we do the similar things for MPC? And absolutely you can. And we propose an algorithm called DelMPC, a diffusion-inspired annealing for like MPC. So the key idea is in standard MPPI, if your sampling kernel is too large, you have a easy to sample distribution, easy to optimize distribution, but you have bias. The star here is different from the true star. And if your sampling kernel is too small, the P sigma is very close to P0. However, you get stuck in local minimum. And in our DelMPC, we do annealing. We start from this smooth distribution and all the way anneal down to the hard distribution. Yeah. Another interesting thing is this can seamlessly integrate with MPC. Remember, MPC is receding horizon. So we can do it in the receding horizon manner, right? So what do we do is the further future state, the further future action corresponding to large sampling kernel and near future corresponding to the smaller sampling kernel. And in a receding horizon procedure, all the actions already experience the whole diffusion process from the large noise all the way to the small noise. So these two things together really enable interesting result. And this video is a visualization of diffusion. You can see we start from noisy trajectory all the way to preset trajectory via its annealing mechanism. And we enable this very big jumping forward with payload. And this is like for humanoid local manipulation, the humanoid can push a very heavy box in simulation. All right. And DelMPC enables 50 Hertz torque level preset local mode control using full order dynamics. I want to emphasize it directly rule out in parallel physics simulation. There's no reduced order modeling. There's no local approximation. There's no predefined context sequence. It's basically end-to-end. We directly output torque from this procedure. And it's training free without any data and a plug in and play. You have whatever new cost, whatever new dynamics, the model can immediately give you some new result. And it allows zero-shot adaptation. For example, in the second video, with a payload, we just adapt the mass and the robot can respond. And it's, of course, fully open source. And the takeaway is scaling online search optimization is also powerful. And just a little advertisement. If you're interested in technical details, go to my student Charlie's talk in today's locomotion seminar, 4 p.m. in 30 minutes in Wing Hall. All right, last technical slides. Not only MPC, we can do the same thing for TO, for trajectory planning, for trajectory optimization, where we can do diffusion style kind of sampling-based TO. And this is a result from humanoid planning, right? You can see the diffusion process, right, from the wrong distribution to the true distribution. And this is a challenging task in model-free RL, right? Push T. We can also do a trajectory optimization to solve the push T problem using this kind of annealing diffusion style idea, right? And we can also combine this with data, even imperfect or invisible data. The idea is data can steer the diffusion process. You can mix the score from the model and from the data. And here's the example. We basically use this is the maze navigation problem. We use the RT to generate that demonstration using wrong dynamics, right? The green trajectory here is demonstration from RT, which is invisible. And our model can adopt this to steer the diffusion process and generate this feasible trajectory. All right. And let me summarize the talk. Today I present this generalist aspect versus physics agility aspect. And two parts. Part one, I introduce humanoid robotic control using sim-to-real model-free RL. And the second part, I discuss the limitation of this framework and how to go beyond via learning control in dynamics level, policy level, and program level. I think the most important takeaway is we need structure scaling plus dynamics and physics. And for all the reference, you can check out in my group's website. And finally, let me thank a bunch of people. First audience today, and the Car Lab, all the members here. This is like skiing last year in Boys Park together with Andrea's group. My group even is also pretty agile. And also like amazing Samuel collaborators, Chang Liu, Chris, Guanan, Basti, Hovey, Jeff, Ding, Max, and John. Okay, thank you so much. And I'm ready to. Jeff, yeah.
Yeah, I want to go back to the H2O stuff at the beginning and ask about forces. And so maybe one example where this is relevant is when you pick up the box.
Yes.
And so if you only get the kinematics
No.
during the video, that the teleoperator didn't move their hands.
Very
to
fast. Yeah.
They move their hands together. So my question is, are they creating the force by over moving?
Exactly.
Is there somewhere
Exactly.
in the learning process
Exactly.
that does or could learn the forces as well?
Exactly. So the current simulation training pipeline is not aware of any object interaction. So it's very similar to mobile aloha. The why can still works because of human feedback. Human observe, okay, you want to lift the bottle, it get down, you just feedback to raise it up. So I don't think the current pipeline is aware of force. Our group are working on that, how to make it explicitly adapt to this physics information like force. Yeah.
Do you think there's any way you could bring the RL into that imitation so that the RL would make the adjustment for you and figure out that it won't be able to hold the box unless it adds force? Is that possible?
I think so, but we need to change the pipeline. Remember in this figure, the pipeline is kinematics level motion imitation.
Right.
If we want to do that, you probably need to introduce all this perturbation force and object.
Right.
And unfortunately, there's no data set like AMAS with physics. So I think that's challenging but interesting for sure. Yeah.
By the way,
Thank
amazing
you.
work. I would like to focus on the last part, the annealing.
Mhm.
Amazing connection with the diffusion. One question, maybe I missed this, but this is all real time, like the control.
Yes, we do 50 hertz in real time. However, only for quadruped. For a humanoid, we can only do 10 hertz because the number of contact points is too many. We use Mujuko MGX. It has some limitations. Yeah.
Usually in the vision, like we see that.
Yeah, but this, you remember, like MPC is receding horizon. You don't have to do diffusion like one shot, right? You can leverage the temporal structure and have this kind of receding horizon diffusion. Yeah, or streaming diffusion. Yeah.
You mentioned that you're not linearizing.
No. We directly sample in the original MGX simulation without any linearization or reduced order modeling or predefined context sequence. End-to-end. Yeah. Question? Yeah. Yes, we actually so the robustness part is too much, honestly. It's more like stationary robustness. So when the robot is standing or do manipulation, dynamical robustness is harder. We didn't try. Yeah. Maybe it works. Maybe it will fail in some tests. Yeah. Question?
Yeah, it's really cool work. I'm curious as to if you compare like the last assembly-based MPPI, like the promotion stuff, with the jumping paper.
Yeah.
Is there anything that like could you get the same results using just MPPI with a better like sampling as you do with this, or is there any like fundamental difference between training like RL and then? Yeah, I'm curious as to like.
Yeah. I got your question to rephrase. If for this kind of like jumping or parkouring, can we just do pure model-based MPPI stuff or something-based MPC? Unfortunately, I don't think so in current limit computation, because again, this procedure is we didn't do it on board, by the way, it's off board and 50 hertz. In my opinion, we need both scaling online and offline. In my opinion, the combination of some online optimization and offline training is the best. So you learn either a nominal policy or value function or whatever from offline learning, and you have some online refinements. In my opinion, that's the best. Yeah.
Thank you. I wonder if you could explain why transformer-based dynamics are better than
No, yeah, it's just empirical. Yeah, here we choose transformer because it's really easy to scale it up to 100 million data points, right? Because this technology is very mature. If you use LSTM or RNN, you need to, this is not very mature. But fundamentally, I don't think transformer is the only solution here. Sorry. Sorry, can you say again? What's the difference between? Very good question. So the intuition is like, in my opinion, the advantage of reinforced learning is flexibility. It can handle all this high-level decision making. For example, this is a great example, I think, right? If the gap is too large, the RO need to basically tell the robot, okay, you need to take a middle step. If the gap is short, you one step, you can just do it, right? And that's, in my opinion, the advantage of a learning-based approach. And for the low-level QP, it's just doing tracking. It's optimal control. It needs precision and robustness. I don't think you really need this high-level decision making. So in my opinion, it's just like why this works very well is we combine the advantage of learning, which is generalizing to different scenarios, and feedback control, which is robustness and precision. Yeah. So the RO is for high-level decision making. Like think about if you play any sports, you are probably doing similar stuff. You have one system for high-level right strategy. You have another system for muscle control or whatever. Yeah, that's kind of the intuition.
Hi, thank you for your fantastic talk. So I wanted to discuss about the any car paper. So there we train one dynamics model across many car embodiments.
Yeah.
We don't tell which embodiment it is, right?
No, it's purely in context adaptation. Yeah.
Because it's just a big, like a recurrent, like has access to long history, let's say, right?
Yeah, 500 steps.
And then the state here is just like how I'm moving and
Yes.
how I'm maybe bouncing up and down, but there's no visual input here, let's say.
No, yeah, very good question. It's not vision based so far. Yeah.
But basically the idea is that now and it's going to be able to specifically identify
In context adaptation, yes.
and predict what to do to achieve us.
Exactly. But we are interested in adding vision here. You can definitely condition this on some perception, right? Make it better. And by the way, this history is a noisy state and action. We never ask the robot to have access to the true state. This X hat is basically from SLAM, from VIO, from whatever state estimator you have. This is like history of state estimation, the history of action.
And it's a goal condition policy that tells you I want the car to go to this location or.
Oh yeah, we actually once we learn a model, we didn't do RO, we do a sampling based MPC, right? Once we learn a model, we just use something like MPPI to do the control. So it can generalize to different tasks because you just change the reward, right? You change the reward, you have different trajectory. Yeah.
And can this be used in real cars? Like this?
We are thinking about this. If I got funding, I will do. I will do something more than 116 or 110. Yeah, the original motivation is off-road, right? Yeah.
I think we should take the rest of the questions offline. Thank you so much.
Thank you so much. Yeah.